Hello, welcome today to CE 241 Material Science. Today is our last lecture of the semester. We're going to talk about fatigue. So fatigue actually is a common type of catastrophic failure wherein the applied stress level fluctuates with time. It is critical for different structures. For example, bridges, aircrafts, machine components can be fatigue-prone examples. The term fatigue is used because this type of failure normally occurs after a lengthy period of repeated stress or strain cycling. Fatigue failure can occur under fluctuating cycling stresses that are considerably lower than the tensile or yield strengths of the material under a static load. Applied stresses causing fatigue may be axial, tension or compression, flexural, bending, for example, or torsional twisting. Here you can see examples. The first one is bending. The second one is actually a torsion twisting. And the third one is basically a compression tension example. The nature of fatigue failure is actually also very important. Fatigue failure is actually brittle-like. Relatively little plastic deformation occurs, even in normally ductile materials. This means sudden and catastrophic failure, which is something we for sure don't want in civil engineering structures. It causes 90% of all failures of metallic structures. Polymers and ceramics, except for glasses, are also susceptible to this type of failure. Fatigue failure proceeds in three distinct stages. The first stage is crack initiation in the areas of stress concentration. The second stage is propagation of this crack. And then the final stage is catastrophic failure, which is sudden and complete, and it doesn't give any warning. Ordinarily, the fracture surface is perpendicular to the direction of an applied tensile stress. So here you can see variation of stresses that can cause fatigue. The first one is a reverse stress cycle. Stress alternates from a maximum tensile stress to a maximum compressive stress of equal magnitude, and mean stress is 0. The second one is a repeated stress cycle. This basically maximum and minimum stresses are asymmetrical relative to 0 stress level, and you have a mean stress and a range of stress and stress amplitude. And random stress is the last one. Basically, it is just random. When we talk about cyclic stresses, the repeated stress and reverse stress, basically the main difference is the mean. And cyclic stresses can be characterized by maximum, minimum, and mean stresses, and the range of stress and the stress ratio. So the range is basically max minus min. Mean is max plus min divided by 2. And R is the stress ratio of stress min to stress max. For reverse stresses, R is actually minus 1. We carry out fatigue tests to determine fatigue performance of our materials. These tests are carried out to determine the stresses that can be applied over a specific number of repetitions, or the life under a specified stress level. The general procedure of a fatigue test is basically like this. You first subject your specimen to a cycling stress at a relatively large maximum amplitude, usually around 2/3 of the static tensile strength, and then you count the number of cycles to failure. And then you repeat on other specimens at progressively decreasing maximum amplitudes. And finally, you plot the data as stress amplitude versus number of repetitions, a logarithmic of number of repetitions. The stress values are normally stress amplitudes, but sometimes max or min values are also plotted. In a fatigue test, stress versus number of load repetitions is plotted to obtain Ascent curves. These are also known as Wöhler curves. There are two distinct types of Ascent curves, with fatigue limit, also known as endurance limit, or without an endurance limit. So let's go through the curves without an endurance limit first. A material that does not display a fatigue limit is actually very common. In most alloys, the stress decreases continuously with number of repetitions. In these cases, the fatigue properties are generally described by fatigue strength, which is basically the stress at which fracture occurs after specified number of cycles, and fatigue life, number of cycles to fail at specified stress level. But some materials display a fatigue limit. It is the maximum stress amplitude below the which material never fails, no matter how large the number of cycles is. Fatigue limit occurs for some ferrous and titanium incorporating alloys. In these cases, the SN curve becomes horizontal at large number of repetitions. For most steels, this value is around 35% to 60%. And fatigue limit is basically maximum stress that can be applied repeatedly and infinite number of times. To briefly summarize. Here on this graph, actually, you can see the horizontal portion at large ends. This is your fatigue limit. So when you have a fatigue failure, there are three stages. The first stage is crack initiation in the areas of stress concentration. Then you have incremental crack propagation. And then you have final rapid crack propagation after crack reaches this particular critical size. So the total number of cycles to failure is actually sum of these cycles at the first and second stages. So initial cycles and then initiation cycles and then propagation cycles. Cycles to failure is basically sum of the initiation and propagation cycles. At low loads, which is also known high cycle fatigue, initiation is relatively high. So you need to repeat many times to initiate the crack. But with increasing stress level, the initiation actually becomes easier and propagation starts to dominate number of cycles. Here on the bottom, you see actually an image that is of an aluminum crank arm fractured due to fatigue. The dark area shows slow crack growth, and the bright granular area is the sudden fracture. There are various factors affecting the fatigue behavior. Of course, the quality of your material, environmental conditions, including temperature and corrosion, range of stress, mean stress, and your frequency of loading. Also, surface effects is critical as most cracks starts from the surface. And you also need to make sure you have good design. So you have to avoid sharp corners if you are worried about fatigue. Round corners actually are much better for fatigue resistance. So let's talk about two main factors that affect the fatigue behavior. The first one is mean stress. As you increase the mean stress, actually you make your material to fail more easily. Here you see three curves on the left. The green one is the highest and red one is the lowest mean stress. As you increase the mean stress, actually you increase the probability of failure. So number of cycles decrease. Here, I hope you see my mouse cursor, or maybe I can open this annotation. Here, okay, let me try this. Here, actually, this is the number of repetitions. What you see is at a higher mean stress, the material fails at a lower stress for the same number of repetitions, and material fails at a higher stress for the same number of repetitions at lower mean stress. The second curve actually shows two different surfaces, as surface is very critical on fatigue behavior. Cracks most of the time start from the surface. The red one is shot peened, and the blue one is a regular surface. Shot peening is a cold working process used to produce a compressive residual stress layer and modify the mechanical properties of metals and composites. It entails striking the surface with shot. Shot is basically round metallic glass or ceramic particles with a force sufficient to create plastic deformation. So surface become a little bit rougher. So as you see, when you improve the surface, you actually improve the fatigue performance significantly. Okay, let's solve a question. Fatigue test results of a material are shown below. Can you estimate the ultimate static strength of this material and the fatigue limit? And also assume that this specimen has a 14 centimeters square cross-sectional area and it is subjected to a maximum repeated load of 2800 kilograms. And how many repetitions later it will fail? So please pause the video before watching the solution. Okay, so the first one is easy. So 0 repetitions. So 450 kilogram force per centimeter square. And the fatigue endurance limit, well, we have to approximate. So it's around 150 kilogram force from the graph. Let me open this and try to draw this. So this is our fatigue limit. And the last one was, the cross-sectional area was 14 centimeters square. Our load was 2800. So how many repetitions later it will fail? First thing, you calculate your stress. So 2800 divided by 14 is 200 kilogram force per centimeter square. So log n equals to 2.7 if you check. Of course, from this graph, you cannot read it very carefully. So this is roughly speaking 2.7-ish. So log n 2.7, then you actually solve for n as around 500. Okay, another question. We have our fatigue data. So this is stress amplitude and cycles to failure. The question asks, can you plot an SN curve using this data? Can you determine the fatigue strength at 5×10⁵ cycles? And can you determine the fatigue life for 200 megapascal? So please pause the video before continuing. Okay, first thing is first, let's plot our data. So our X is log cycles to failure and our Y is stress amplitude. This one is a little bit different, so we don't know exactly, it's not a logarithmic paper. So we have to be a little bit more creative. So first thing is first, fatigue strength at 5×10⁵ cycles. 5×10⁵ is actually in log scale 5.7. So here I am at 5.7, so I go up. So fatigue strength is around 250 megapascal. And the second one says fatigue life for 200 megapascal. So I'm here, so I go here and I go down. It is roughly 6.3. So 10 to the power 6.3 is roughly 2 times 10 to the 6 cycles. Let's solve another question. Again, we have our stress amplitude and cycles to failure data. Please plot the SN curve. What is the fatigue limit for this alloy? Can you determine the fatigue lifetimes at stress amplitudes 230 and 175 megapascals? Can you estimate the fatigue strengths at 2 times 10 to the 5 and 6 times 10 to the 6 cycles? Please pause the video before continuing. Okay. So I hope you got this one right. Here is our plot. Again, this one is not a logarithmic graph, but no worries, you know how to convert this if it is not a logarithmic graph. So fatigue limit is the stress level at which the curve becomes horizontal. Here, actually, we know it exactly. This is the part where it gets horizontal. Oh, sorry, what happened? So let's go back. Here, we already know it's 193 from the data. So here is our fatigue limit. The curve becomes horizontal. And part C actually asks for the fatigue lifetime at stress 230 and 175. So let's do this. Fatigue lifetime at 230. So this is 230. I go down. And this is roughly speaking 5.7, which is 10 to the power of 5.7 is roughly 5 times 10 to the 5 cycles. And then let's check 175. This is 175. So it is actually below the fatigue limit, which was 993. So it is basically infinite, so it never fails. And part D actually asks for fatigue strength at 2 times 10 to the 5. So let me clear these lines. So 2 times 10 to the 5 is log n, it is 5.3. So I'm here at 5.3. So this is basically 2 times 10 to the 5. Oh. Oh. So it's roughly speaking 240. And then it also asks fatigue strength at 6 times 10 to the 6. 6 times 10 to the 6, if you take log, it's 6.78. So it's here. So I go left like that. So it is around 205. So you can also use a logarithmic paper too, but I wanted to show how to use the same data in a different way. Okay, great. So let's continue. Okay, different question. So what would I do if I use 2 different stresses? So stress 1 and stress 2. So let's do this. We have a beam and we subject it to reverse cycles at stress 200 megapascal. And we actually do 5 times 10 to the 2 cycles. How many additional cycles can the beam withstand at 150 megapascal? I also wrote the N values for 200 and 150 megapascals. I also have the graph. You can also read them from the graph. For N 200 megapascal is 1.65 times 10 to the 3. And 150 is 105 times 10 to the 4. And to solve this question, please use a rule called Miner's rule for fatigue under varying stress, which is basically number of stresses cycles you have gone through in first stress divided by its lifetime plus number of cycles that you have gone through the second stress and lifetime in the second stress. These should add to 1. So 5 times 10 to the 2 divided by 1.65 times 10 to the 3. This is the 200 megapascal portion plus number of cycles under 150 divided by lifetime under 150 megapascal, which is 105 times 10 to the 4. This should add up to 1. So you can solve 4 and 2, which will give you 7,318 cycles. Sorry, my son is a bit bored. If you are hearing his voice, he's a baby, so he kind of misses his mother right now. Okay, let's continue. Now we will do a different question. We have 3 identical fatigue specimens, A, B, and C, and they are fabricated from a non-ferrous alloy. Each is subjected to one of the minimum maximum stress cycles listed below. The frequency of these are the same in all these 3 tests. So specimen A, actually it is from 450 to minus 350. And specimen B gone through 400 megapascal to minus 300 megapascal. And specimen C went through plus minus 340. Can you rank the lifetimes of these 3 specimens from the longest to the shortest? And also, can you justify this ranking by using an SN plot? Please pause the video before going on. Okay, in order to solve this problem, first of all, we need to compute mean stress and stress amplitude for each specimen. Mean stress is basically the average. So for A, B, and C, it is calculated as 50, 50, and 0, respectively. And we also need to calculate the stress amplitude. It is max minus min divided by 2. So for A, it is 400 megapascal. For sample B, it is calculated as 350 megapascal. For sample C, it is 340 megapascal. So just looking at these, I can really clearly, easily say C larger than B, larger than A. Okay, let's go through them in a graph. So here it is. We have C and we have A and B. So the mean stress for C sample is 0. So it has a lower mean stress. And that means it can actually have a longer lifetime. For specimens A and B, you have a mean stress of 50 megapascal, which means they will have for sure a shorter lifetime. So we know C wins. Oh, plus, plus also the average amplitude, amplitude calculated for C is 340 megapascal, which is also lower. So for sure, C will have a longer lifetime. And here, actually, this is the mean stress, 0. And this is what happens if you increase the mean stress schematically. And also, this is 340. So here we have 350, and here we have 400. So this is A, which will be basically have a shortest lifetime. Then we have B, and then finally we have C. Okay. So this was the last lecture of the semester. I hope you have a great year, happy, healthy, and for sure happy and healthy, and a lucky new year. And hope to see you in person soon. Best of luck in your finals. See you. Bye.